What I'd like to do now is take a look at a couple of string hashing algorithms. The first is an incredibly naive implementation, and what it does is it sums the ASCII value of each character in the string and returns that sum as the hash value. For example, we have the string foo. The ASCII values of f are 102, and the O and the O are 111 respectively twice. So those three values added together equal 324, and that would be our hash value for the string foo. Now, when you think about our four measurements for a hash algorithm, this is stable and it is efficient, but it's really a terrible algorithm. First of all, it's not very uniform, and it's not very uniform because the order of the characters in the string don't affect the value of the hash. So FOO hash is the same as OOF. That is not a characteristic we're looking for in a hash algorithm. And this algorithm is ridiculously not secure. I mean, if you're given the number 324, you can just start pulling out ASCII characters until you find the value you want. There is nothing even remotely secure about this. So it is stable, it is efficient, it's a single pass, it's just integer math, but it's not a good choice. It's about as simple of an algorithm as you can get, though. And what it really demonstrates, though, is there is a very, very simple way to derive an integer value from a string. So let's look at a slightly better algorithm now. This is a little bit better, and what it does is it folds every four characters into an integer. And remember, we can do that with ASCII because each ASCII character is 8 bits, 1 byte. An integer is 32 bits, or 4 bytes. So we can take four ASCII characters, cram them together, and say, hey, it's an integer. And that's what we're going to do here. So we have a string, it's a little lorem ipsum. And we're going to take the first four characters. And when you take the bytes of those characters and just cram them together into a 32-bit value, we end up with a 1.7 billion value. Now, at the moment, that's our current hash value. So now let's look at the next 4 bytes. They have their own value. Let's add our current hash value with the new value. Now it wraps back around because we're doing 32-bit math, so when you add two really big numbers in the 32-bit space, they wrap around to a negative value. Let's look at the next 4 values. They create their own large integer, which we add, and now we're still with a negative number. Take the next 4, cram them together, get our 4 bytes, add it to the current hash, and then we take our next 4, but there's only one, so it's all zeros and then one value. That ASCII value is 114. We add it, and we have our hash value. So ultimately here our hash value is a 1.7 billion number. Now this is stable, it's pretty efficient, and it has good uniformity. The ordering of the characters in the string directly affect the hash value. So FOO, foo, is different than OOF. But it's not secure. It's not even remotely secure. We could treat this as basically additive. But even though this algorithm isn't secure, it's good enough for what we're going to be doing for string hashing. So let's go ahead and move on and just look at a comparison of some of the hashing algorithms we know about, and a few we don't know about, but which come with the .NET framework. So first, don't write your own hashing algorithm. Okay, the .NET framework ships with several. They're good. These are things thought out by mathematicians, by really smart guys over many years. They're vetted out by the community. Hackers have attacked them for years. A lot of the problems have been found, and solutions are being derived from those. Don't create your own hashing algorithm. Okay, I can't stress that enough. The next thing is to pick the right hash for the job at hand. Look at the characteristics of the problem space you're working in and pick the hashing algorithm that applies best to it. Let's look at a couple hashes here. And now bear in mind, my judging of the stability, uniformity, efficiency, and security are really fluffy. I mean, these are debatable points, and I don't want to dig too deeply into them, but they're just some kind of high-level thoughts on it. The first thing we looked at was our additive hash. This was the hash that summed up all the values in the string. It was stable, it was efficient, not uniform, not secure. Our folding hash, this was the hash that crammed 4 bytes at a time into an integer value. It's stable, it's pretty uniform, certainly more uniform than the additive hash. It's efficient, it's a single pass through, it's integer math, but it's not secure. CRC32 is a really common hashing algorithm. Like the folding algorithm, it's stable, uniform, and efficient, but it's not a secure algorithm. In fact, there are instances where the CRC32 algorithm has been the root cause of a compromise. The MD5 hashing algorithm is very commonly used, and it's provided with the .NET framework. Now, it's a good balance of stability and uniformity, and I have a red X for efficient, and I did that because as a comparison to folding in CRC32, it's not that efficient, but really, it's a good hash. I mean, you can do this a lot. You can do it millions of times really quickly, no problems. If you're looking for a hashing algorithm and you don't need security, take a look at the MD5 algorithm. See how the performance characteristics work for you. Finally, we have like SHA2. And I call out SHA2 specifically because SHA1 has known problems. So SHA2 is stable. It's uniform, it's secure, it's not that efficient, but remember, security comes at a cost, and that a cost is going to be efficiency. So it's not a surprise that it's not that efficient, but it's a great choice if you need secure hashing. Take a look at the .NET Framework classes for it. If you need a secure hash, it's a great starting place.